this was a question from the textbook I looked at earlier, but I thought a different approach could have been a little bit simpler. Sometimes when you get questions like this that ask you to compare things, it can be convenient to just assign a number to something. So here we have a cat with a right mass of 5 kilograms and a mouse with a mass of 35 grams, so 0.035 grams. And you want to know you're only told the cat's kinetic energy is 100 times the kinetic energy of the mouse. So one other way to do it that I looked at is you just say let the velocity or sorry speed of the mouse be 1, right? Just give it that value, and then you're going to get the speed of the cat as some other number, and then you can just compare those two numbers. So if I just assign the speed of the mouse as 1, and then I can actually calculate a kinetic energy for the mouse, multiply that by 100, and figure out what the speed of the cat is. I get the same number when I just leave everything as sort of a fraction. So that could just be, just kind of a general problem solving approach. Another one, this one came up during the async time. Someone asked about. This is completely wrong, though, if you look at the solution in the book. So it might be something you'd wonder about. A child tosses the tennis ball straight up into the air with an initial speed of 11 meters per second. I don't think that really matters. Determine the maximum height. Absolutely, you know how to do that. You can even do that with dynamics. Sorry. But part B is where it's wrong. You're asked to sketch a graph of the potential energy versus time. And then part C, you want to sketch the kinetic energy versus time. So if you sketch these, they should look like this, right? The potential energy, now it's up to you to say where h equals 0, but it's probably most convenient to define the height of 0 right at the point where it's thrown from, let's say, or the ground, right? So remember, the equation for gravitational potential energy is just mgh. The mass of the tennis ball doesn't change, right? G doesn't change. So basically, you're just graphing the height of the tennis ball. So as it goes up, right, it gains height, it gains gravitational potential energy, right? And then it comes back down. And you'll notice the connection between this and the kinetic energy one, right? Kinetic energy, it starts with a lot of speed, right? Because you're throwing it up. It's got the most speed it's going to have. And then that's going to decrease it may not go all the way to 0 if this is not thrown, I don't remember now, straight up in the air. So yeah, it is going to be 0, right? Because it's not going to have any horizontal velocity. So it's going to go to 0 at its maximum height, and then, so basically it's a graph of the speed versus time. And you'll note how these two are connected. One other question we might look at here, number 9 on page 181. We've got a gallon of gas contains about 1.3 times 10 to the 8 joules of chemical potential energy. So just another type of potential energy. We want to determine how many joules of chemical potential energy are stored in each liter of gas, which our gallon, which is 3.79 liters. Calculate the height that the amount of chemical potential energy in 1 liter of gas could raise all the students in your class if it was all converted to gravitational potential energy. And this is, you'll have to make some assumptions here, right? So first, how many joules per liter? 1 liter has 1.3 times 10 to the 8. So divide that by 3.79. And that gives you 3.43 times 10 to the 7 joules per liter. And as just kind of a check, I know that there's more, or a liter is less than a gallon, right? You need almost 4 liters to make a gallon, and this number is less, right? Each liter of gas has roughly 34 million joules, right? So here's just some rough assumptions. Assume about 30 students and assume about 55 kilograms per student. Right? It's a reasonable assumption. I don't know, but again, you're just making an approximation, and this is one of the most useful things about physics in general. If you go more to that engineering side, is like we have to make some simplifications and some assumptions. So we'll just take some rough numbers to get kind of an estimate. Then we're just going to go with conservation of energy, right? Now that we've got a rough mass estimate for the entire class, we can say, look, we're going to convert all of that chemical energy into gravitational potential energy, right? And so mgh is going to have to equal all of that chemical energy, which we said is 3.43 times 10 to the 7 joules. Substitute in the mass in g and solve, and you get a height of about 2 kilometers, right? Not bad. Means if we were able to convert all of that energy in a liter of gasoline, we could raise the whole class to about 2 kilometers. Now, doing that is not always that simple, and you usually don't get 100% efficiency. That is, you're not able to convert all of that. You're going to have a lot of other losses like heat and whatnot. So probably not going to get us all of that height, but just, in theory, that's what you could do, which is kind of cool.